If you step back and look across biology, the pattern is surprisingly consistent. Animals use fructose metabolism to survive scarcity. Fruit uses fructose to signal ripeness and urgency. Human history shows what happens when that signal becomes constant. Across species, across food systems, across centuries, the same rule keeps appearing. When fructose metabolism stays on too long, cellular energy production falters. That energy failure is the common thread. And in this chapter, we're really talking about three organ systems that sit in the center of that failure. The gut, where exposure begins, the liver, where the signal is amplified, and the kidneys, where conservation is enforced. Each plays a different role in the same survival program. Cells become fragile. As we discussed earlier in the series, fragile cells don't stay isolated. They scale into fragile systems. And that's where history, nature, and biochemistry all start converging, because when this survival signal remains active, it doesn't produce one isolated problem. It establishes a contagious fragility that precedes chronic disease. What follows becomes a recognizable pattern. The first place that pattern becomes visible is metabolic dysfunction. Type 2 diabetes, fatty liver disease, gout, chronic kidney disease. We tend to treat these as separate epidemics, different diagnoses, different specialities. Even within research, they're often studied in isolation, which makes the shared pattern harder to see. But biologically, they travel together, not because one causes the other, but because they're shaped by the same upstream pressures acting on cellular energy. Chronic fructose metabolism is one of the most powerful and pervasive of these pressures, a near universal drag on cellular energy, though it's not the only one. And that distinction matters because fructose metabolism isn't a side effect, it's a program designed to do very specific things: store fat, conserve water and salt, lower energy output, drive hunger, because in a world of scarcity, that suite of responses keeps you alive. In a world of constant abundance, the same program becomes pathological. One of the strangest features of metabolic diseases is this: people gain fat while feeling starved. They eat plenty, but they feel tired. They have fuel everywhere, yet little usable energy. The problem isn't how much fuel comes in, it's how much gets turned into energy. So then start thinking of it like a narrow funnel. Fuel pours in from the top, but only a trickle makes it through. Everything backs up above the choke point. That's what impaired energy production looks like. Fructose metabolism drains cellular ATP and suppresses mitochondria, not by removing fuel, but by slowing the conversion of fuel into usable energy. When cells can't make enough ATP, they don't register abundance. They register shortage. And the response becomes automatic. Hunger rises, energy output falls, storage turns on. Fuel remains plentiful, but access to it is blocked. And so glucose lingers in the blood. Fat stays locked away. Cells remain energy poor. And soon, insulin resistance emerges. Not as a defect, but as an adaptive brake. It slows fuel entry into cells that can't safely process more. That's why simple calorie restriction, appetite suppression, or even weight loss medication often fails to restore metabolic health. The system isn't broken, it's just conserving. Among this cluster of diseases, fatty liver stands out, not because it's the most visible, but because it sits at the center. After absorption, fructose is delivered primarily to the liver, and hepatocytes are loaded with high-capacity fructokinase, allowing fructose to bypass normal metabolic governors and be processed rapidly. That combination matters. Carbon is funneled into fat production, even without excess calories or weight gain. As fat accumulates in the liver, insulin signaling degrades. Lipids spill into circulation, metabolic risk rises across the system. And that's why fatty liver predicts diabetes and cardiovascular disease, even in people who appear lean. It's not a cosmetic problem, it's a metabolic bottleneck. Every cycle of fructose metabolism generates uric acid, and originally this was useful. Uric acid sat at the center of the survival response by deliberately slowing energy production. By suppressing mitochondrial output, it helped conserve fuel, salt, and water. It supported circulation during dehydration. It reinforced survival under scarcity. But critically, the kidney was part of that design. The kidney interprets uric acid as a conservation signal. It responds by retaining salt and water, tightening energy use, adjusting filtration to support survival when resources are limited. In a modern world where scarcity is rare, the same loop becomes a liability. Inside cells, uric acid increases oxidative stress and suppresses mitochondria further, deepening ATP depletion. And as kidney handling degrades, uric acid clearance falls, reinforcing the signal and locking conservation in place. Systemically, this then spills outward, burdening renal function and stiffening the vascular system, effects that become more visible later in cardiovascular disease. So the signal that once protected energy balance now amplifies energy failure. Short-term adaptation, but long-term damage. The gut is the first tissue exposed to fructose. Enterocytes can metabolize fructose, but their capacity is limited. When intake exceeds capacity, energy stress appears locally. This alters barrier function, transporter expression, and immune tone. This actually might explain why many food intolerances cluster here. When cellular energy falters, the gut becomes less selective in how it handles carbohydrates and proteins, creating symptoms that are often misattributed to the food itself. But systemic metabolic dysfunction doesn't originate in the gut. In many cases, early gut stress actually acts as a brake. Discomfort, bloating, or intolerance leads people to avoid fructose-rich foods naturally, reducing the downstream exposure. The disease pattern emerges when that protective signal is bypassed. It takes hold once fructose flux is amplified in the liver, and conservation is enforced by the kidneys. The gut is the entry point. The liver becomes the bottleneck, and the kidneys determine whether the system just lets go. When this runs long enough, a characteristic pattern emerges: central fat accumulation, high triglycerides, low HDL, hypertension, insulin resistance, elevated uric acid, declining kidney function. These aren't random risk factors. They're actually a visible footprint of one metabolic posture: energy conservation, locked on. Metabolic dysfunction is simply the first and clearest expression of chronic fructose metabolism. It appears before heart disease, before neurodegeneration, before cancer. It sets the terrain. Fructose metabolism stores fat to prepare for scarcity, generates uric acid to conserve water and salt, suppresses mitochondria to save energy, drives hunger to ensure intake. All of this makes so much sense in the right context. Problem is just that the context changed. This doesn't end the story. It explains why so many diseases follow. And in the next sections, we'll see how this same energy failure expresses itself in the heart, in the brain, and even in cancer. Not as separate mysteries at all, but just different faces of the same underlying state.